Okay, we're going to look at metal reactivity next. Now, we've already sort of looked at metal reactivity earlier in the year when we looked at the reaction of the group 1 and group 2 metals with water. So we saw that sodium and potassium were already very reactive with water. They really wanted to give away their electrons, which is what we would now call being oxidized, because oxidation is the loss of electrons. So, we talked about those metals being very reactive. Metal reactivity also is really important in terms of thinking about corrosion and what happens with corrosion. It's why if you own a boat, you might have a little sacrificial zinc anode attached so that that is oxidized rather than the actual structural metal that makes up the boat being corroded or rusting away, so to speak. It's also going to be very important in terms of considering how and why batteries work. We'll talk more about that in the next flip lesson, and that will relate to the practical that we're going to do as our design and deconstruct, which will be the assessment for this topic. Let's get in and look at metal reactivity. Okay, so as usual, we'll start with our science understanding here on the left-hand side. There's a lot of stuff here written, but I think the concepts are pretty simple. So remember, the blue is sort of the concepts. The green are the things that you need to be able to do, the success criteria, if you like. So metals differ in their tendency to lose electrons. More reactive metals lose electrons more easily. We talked about that with the reactive metals like sodium and potassium earlier in the year. Which, that loss of electrons is what we now know as oxidation. So a more reactive metal is able to donate electrons to the ion of a less active metal in a displacement reaction. So I'm going to demonstrate what that looks like in a minute. I've made a little video and I'll explain both the chemistry of it and then we'll just show the video of the little experiment. So you need to be able to write equations and half equations for reactions between metal and ion of a less reactive metal. So it's basically using those concepts of oxidation and reduction that we looked at last week and writing half equations, but these half equations tend to be very simple ones to write because normally we only really have to worry about balancing out the electrons. We don't normally have to worry about the hydrogen and the oxygen and all that sort of thing. The reactivity can be represented with this metal reactivity series, which I've got here, which goes from the most reactive to the least reactive. And I'll go through this in the prac that I do, but basically the way that we determine whether a reaction is going to occur and what that reaction is from looking at this metal reactivity series. So when we look at in the prac, we are going to look at zinc and copper. We could have picked any two here. I'll just bring this down here. I think I'll do this down at the bottom. Now what we see there is zinc is more reactive. So that means zinc wants to be oxidized. So if possible, the zinc wants to go from being the metal to lose its electrons, and zinc forms a 2+ ion. You don't need to remember that. You'll always get told, unless if it's a group 1 or group 2 metal, you're supposed to remember group 1 form a +1 charge, group 2 form a 2+, but with the transition metals we'll always give you information. No oxygen or hydrogen, so to balance that out we just add the 2 electrons. So that would show that the zinc there is being oxidized, it's losing its electrons. The copper is less reactive. So that would prefer to stay as the metal. So in the experiment I'm going to do at the moment, we're going to put some zinc into a solution of copper sulfate. So copper sulfate has copper 2+ ions with the sulfate ions. And what will happen there is that will be reduced, so it will gain electrons to form copper metal. So if we take a piece of zinc and put it with copper ions, that's the reaction that will happen. Now, if we did the opposite, if we took a bit of copper and put it with some zinc ions, well, the copper is already reduced. It's already got its electrons. The zinc is already oxidized. So then we won't get any reaction. Nothing will change. So if we had tried to do zinc ions and we had put them in copper metal, basically there we will get no reaction because the zinc is more reactive and it's already oxidized, and the one that's more reactive wants to be oxidized. You'll see what this looks like when I do the demonstration in a minute. And that same theory would work for any of the metals along there. So in the final one, we need to think about the reactivity of the metals in both water and acid. So generally speaking, these metals here, potassium, sodium, lithium in particular, will all react vigorously with water. They're very reactive. What happens in those reactions is if we have sodium metal and we react it with water, it obviously wants to lose its electrons to form the sodium plus ion, and that releases an electron. And if you remember, with the sodium or the potassium, we often quite got the ignition of the flame. It caught fire. And the reason that happened is, in this case, it was reacting with the water to make hydrogen gas. This one here is a little bit tricky to think about the balancing, but we can just use the half equation method. So we've got to add a water on this side to balance out the oxygen, and then we need to add 2H plus to balance out the hydrogen ions, and then we have 2 electrons here to balance out the charge. So what we have here is the sodium is losing electrons, it's been oxidized. The water has been reduced, it's gaining electrons. This is producing the hydrogen gas, which is why that we can get the ignition of that hydrogen gas if that gets hot enough, because this is a very vigorous reaction that generates a lot of heat. Now, I guess these ones that react with water will also react vigorously with acids, but right through this area here, these will all react with acids. So you might remember doing, oops, don't know what happened there. Let's just try doing it. Just move that out of the way. These will all react with acids. So you might remember doing the pop test with magnesium, where you put a bit of magnesium into an acid. In a sense, what happens there is the magnesium is oxidized to form magnesium ions. It dissolves. Balance out the charge. We need 2 electrons. The acid, which is basically something that can donate hydrogen ions, H plus, goes to form hydrogen gas. So we need 2 of those plus 2 electrons. We have electrons being lost here, oxidation, electrons being gained here, reduction. That hydrogen gas we can detect through the pop test. So, that's talking about the reactions of the metals with water and acids and how vigorous they are, which is that dot point, and then that one is about doing the half equations. So apart from that, what I'll do is now add the video of doing this practical here with the zinc and the copper so that you can just see what this looks like. If I can find it on video, I also have a demo of doing, it's actually not magnesium in the pop test. I have it doing it with zinc and acid, which is the one which some of you seen me do, where we do it in the balloon and then we ignite the balloon, the hydrogen gas in the balloon, which is this similar type of reaction that's happening. So I think I have that on video somewhere. I'll have to go and look and see if I can find it and add that to this flip lesson as well. Okay, so we've got two metals here that we're going to look at, zinc and copper. Copper is at the less reactive end of the metal reactivity series. So it's harder to oxidize, it's more easily reduced. And zinc is around about the middle, but it's a little bit towards the more reactive end of the middle. So zinc is easier to oxidize, obviously, than copper, and harder to reduce from zinc ions back to zinc metal. So if we take a piece of zinc here and we put it into some copper sulfate, so the copper sulfate solution contains copper ions, so we've got copper 2+ ions here, and we've got zinc metal with no charge. And if we put that into there and just bury that down, just get that under the water, and you can probably almost see the edges of it starting to go black, but we'll leave that there for a bit longer. And then we're also just going to take a piece of copper and put that into the zinc sulfate solution. Just move that so it's a bit better in the camera. There you go. Okay, so as you're watching that, you can probably see that bit of zinc is going much darker. So what's happening there is, because zinc is more reactive than copper, the zinc is being oxidized. So the zinc metal is losing its electrons. Oxidation is the loss of electrons to form zinc ions, and the copper ions are basically accepting those electrons to form copper metal. So what we have is a layer of copper forming on the outside of that zinc as that zinc is oxidized and loses its electrons, gives those electrons to the copper, which gains electrons to form the copper metal. Now, because of the size of the particles in the zinc background, it doesn't look exactly the same as a bit of copper, but if we leave that long enough, you'll see it is a sort of brownish color metal, which is similar in the color to we see there with the copper, which is that brown color as well. So yeah, this is basically demonstrating that metal reactivity series. The zinc is more reactive, so it will be oxidized. The copper is less reactive, so it will be reduced to the copper ions. Over this side, we have copper metal and zinc sulfate, and we don't see any reaction at all. Nothing's happening on this side because the zinc is more reactive, so it wants to be oxidized. So in zinc sulfate, we have zinc ions and sulfate ions. So we already have the zinc 2+ ions. It's already in the oxidized form. The copper is already in the metallic reduced form, so it doesn't really want to change. So then we don't see any difference. So you can see here, this bit of copper looks pretty much the same as what the copper it came from did before it went in. Whereas this bit of zinc, this bit of metallic zinc, obviously what's formed there in the solution doesn't look anything like what we started out with at the start. So if we take that out, we can see, you can almost, it's hard to get the angle right, but just turn that back over, it's just got some texture on it. We can see how that evidence of that reaction has happened with the more reactive zinc in the copper ions. Okay, hopefully that demonstrates the reactive series. We could do that with lots and lots of different metals, and if we get time, we might do some of that in the lab as well. We're also going to demonstrate in the next part how this is also exactly the principle of how we generate a flow of electrons in a battery, how we use a spontaneous reaction. We have a spontaneous reaction here, to create electrical energy. And that's what we'll do in the next section. No, they just zinc metal that's just been ground up into little granules.
Thing.
And then I'm going to pour some concentrated hydrochloric acid. And I'm going to
Deadly sound. Watch out. Watch out, guys. Watch.
If this spills, do not touch it.
Why not?
Henry, look at it.
What the hell?
Holy
Whoa.
That's going straight out the top.
Breathe it in, breathe it in.
Wow, is it gonna pop?
Henry, go put
Is
it
it gonna
near.
pop?
Go put it near.
Yeah,
The first thing you'll notice about this balloon is
Holy.
Whoa!
Whoa!
Okay.